is going to deliver invited talk today. She is hailing from God's own country, Kerala. And she is a BSc Mathematics from St. Joseph's College, under the affiliated college from Calicut University, MSc Mathematics from Cochin University of Science and Technology, where presently she is working. And she is also CSIR UGC JRF NET Fellow during the year 2003. And she obtained her PhD from Cochin University of Science and Technology in the year 2009. Mentioning her professional experience, she is research guide of Mahatma Gandhi University from the year 2014 onwards, and 2 students have been awarded PhD degree, and 4 students are pursuing the research study under her ablished guidance. She is also awarded many prestigious awards, and many achievements are there. She was awarded Best Alumni Award from St. Joseph's College during the year 2019. IMS Prize instituted by Indian Mathematical Society in the year 2013, and Kerala State Young Scientist Award instituted by Kerala government during the year 2012. She also stood as first rank during her MSc Mathematics from the Cochin University of Science and Technology during the year 2002. And she has also completed successfully UGC minor research project during the year 2016, entitled as Study of Various Graph Parameters under Graph Products, and KCST major research project also completed successfully in the year 2019. And looking to her other academic activities, she is the reviewers for mathematical reviews, Central Math, and Bulletin of Mathematical Sciences and Applications. And mention to her association with EDMA, she was also worked as a secretary for 2 consecutive terms during 2016 to 2020, and she has made many processes of EDMA streamline regarding the membership issues, and very much attentive in preparing the minutes and notes of all the proceedings. So particularly being an office bearer of EDMA, I appreciate her contribution. And at this morning, I will like to request her to deliver an invited talk entitled as Gamma Graph of a Graph. Dr. Aparna Lakshmanan.
Thank you, Professor Samyak Vaidya, for that very detailed and kind introduction. So let me present my screen first. I hope the screen is visible and I am audible.
Yeah, both are okay.
Yeah, thank you, sir. So first of all, let me thank the organizers of ICDM 2021, especially Professor Tamil Selvam for his kind invitation and the entire organizing committee, and also to Academy of Discrete Mathematics and Applications for inviting me to deliver an invited talk in ICDM 2021. The title of my today's talk is Gamma Graph of a Graph. I came to know about gamma graph of a graph in 2009, directly from the mouth of the creator, Professor Sridharan. I'm very happy that he's also present here to listen to this talk. It's from him. He's the creator of gamma graph, and it's from him I heard about gamma graphs for the first time, that too during 2008 ETMA annual conference. After that, I wrote a paper in gamma graphs, and then my interest got deviated to some other topics. And for a decade, I didn't touch much on gamma graphs. And now I'm back to gamma graphs due to a question raised by my PhD supervisor, Professor Ampad Vijay Kumar. And yeah, I'm back to gamma graph of a graph. Okay. To begin with, just for the sake of completion, I'm sure all of you will be familiar with the concept of domination number, but in case if there are anyone who is not familiar, let me begin with the basic definition of domination number. Given a graph G, a dominating set is basically a subset of the vertex set, say a subset S of V, such that every vertex in V is either present in S or is adjacent to an element of S. In short, the closed neighborhood of the set S is the entire vertex set. And a dominating set, obviously, if you take the entire vertex set, that satisfies this condition. But we are not interested in that. We are trying to minimize the cardinality of a set which satisfies this property. So a dominating set is minimal dominating if no proper subset of it is a dominating set. And the domination number denoted by gamma of G is the minimum possible cardinality of a dominating set. So just to distinguish the difference between minimal and minimum, here you have the same graph 3 times, and in each drawing, the red vertices gives you a dominating set. As you can see, since there is no universal vertex in this graph, the domination number is not going to be 1. Domination number is 1 only if the graph contains a universal vertex. So we need at least 2 vertices to dominate the graph. Again, if you take these 2 red vertices, you can see that every white vertex is adjacent to at least 1 red vertex. In this case, exactly 1 red vertex. So this is a minimal dominating set. Again, these 2 vertices gives you another minimal dominating set. 1 is not possible, so the minimum possible is 2. And all white vertices are adjacent to at least 1 red vertex. In this case, you can see that this particular white vertex is adjacent to 2 red vertices. So that can also happen. A single vertex can be dominated by more than 1 vertex. If a vertex outside the dominating set is dominated exactly by 1 vertex from the dominating set, then we call such vertices as the private neighbor of the corresponding vertex from the dominating set. So in this case, all the vertices outside the dominating set, in the first case, all the vertices outside the dominating set were private neighbors of 1 vertex from the dominating set, but here the case is different. Again, coming to the third drawing, here you have 3 vertices. And it is easy to observe that if you recolor at least 1 red vertex with a white vertex, then the red vertices won't be a dominating set, because each red vertex is required to dominate itself. If we remove that vertex from the set, then there is no other red vertex to dominate it. So again, this is a minimal dominating set. As you can see here, we have 2 minimal dominating sets of cardinality 2, and here the third one is again a minimal dominating set, but of cardinality 3. That is, it is not minimum. So we can have many minimal dominating sets of different cardinalities, but we are looking for the minimum possible. Again, that need not be unity. Here we have two minimal dominating sets, which gives us the minimum cardinality. And the domination number of this graph is 2. Now, just to mention about the applications of domination number is applied in security systems, in communication networks, in coding theory, in clutter and block clutters, in the theory of matching, in social network analysis. Of course, not limited to this list. The list goes on. Since my topic is gamma graphs, I am not going into the details of the applications of domination number. I just thought of mentioning it. Again, what we have just now heard is domination number, but we have at least 1,000 variations of domination numbers based on the set which is taken as the dominating set. So the first one, obviously the first one is total domination number. The difference is that in a total dominating set, a vertex cannot dominate itself. So it can dominate all its neighbors, but not itself. So what will be the difference? In the case of dominating set, the closed neighborhood of S was V, but in the case of total dominating set, the open neighborhood of S must be equal to V. Now, another way of looking into domination is that of paired domination number. Here, the set S must have the property that the subgraph induced by the vertices in S, the dominating set, must contain a perfect matching. Obviously, paired domination number will always be a multiple of 2. Another kind of domination is connected domination number. Again, the restriction is on the set S. The subgraph induced by S must be connected. Then another variation is independent domination number. Here, the restriction is that the set of all vertices in S must be independent. That is, no two vertices must be adjacent to each other. And as I already pointed out, there are so many variations of domination number. Most of them are having definite applications, and some of them are created just for the sake of creating it. I think the basic motivation to look for such variations of domination number is a paper due to Basco and Tuza in 1990, dominating clicks in P5 free graphs, which was published in Periodica Mathematica Hungarica, in the year 1990. In that, they have posed a problem. Let P be a property of the vertex sets in graphs. Characterize all graphs having a dominating set satisfying property P. This was their question. So this total domination, independent domination, paired domination, and connected domination were all introduced before this paper, this 1990 paper. But we can see that for all these 4 domination parameters, we can always find a dominating set of that property, provided some conditions are satisfied. In the case of total domination, we can always find. And in the case of independent domination, we can always find. But that may not be true in the case of paired domination number. It may not be always possible to find a dominating set such that the underlying subgraph induced by S contains a perfect matching. That happens if there are isolated vertices. If there are isolated vertices in the graph, to dominate those isolated vertices, we need to take them into the set, and they cannot be present in any perfect matching. So there we have a restriction. And if coming to connected domination number, only for connected graphs, there will be a connected dominating set, and for all connected graphs, there will be such a set. So this question can be answered for all those 4 parameters, and motivated from this question, so many variations of domination number were created, and even otherwise, even without looking into the paper, there were so many variants of domination number introduced in literature. So Fundamentals of Domination in Graph is a good text to which you can refer if you are interested in the variations of domination number. So before moving to my topic, let me just spend 1 minute on graph parameters and graph operators, just to distinguish what are graph parameters and what are graph operators. Domination number is basically a graph parameter. A graph parameter can be viewed as a function defined on the class of all graphs to numbers. I have loosely written it as numbers. Usually, that range set is the collection of all natural numbers. In the case of domination number, of course, it is the collection of all natural numbers. Sometimes that range set moves to whole numbers. And I have seen examples where this parameter now moves to rationals and even to real numbers and waiting for new graph parameters, which may lead to complex numbers also. So it's basically a function. You have plenty of examples. Of course, domination number and all its variations are examples of graph parameters. Again, we have, say, radius, diameter, click number, independence number, say, triangle number, so many, coloring number, chromatic number, and all variations of chromatic numbers, etc., etc., etc. All are examples of graph parameters. You give me a graph, I can associate a value to it based on these particular parameters. That is the simple meaning. Now, another thing is graph operator. Graph operator can again be viewed as a function defined from the class of all graphs, but here the range set is different. Earlier, we had a collection of numbers. In most cases, it is natural numbers, and here the range is again the collection of the class of all graphs. And depending upon the operator, there may be restrictions on the domain set as well as the range set. Usually, the domain is the class of all graphs. But coming towards the range, we get so many subcases. Say, one of the well-known graph operators is line graph. You give me a graph, I can find the line graph of graph. The resultant is again a graph. That is the concept of graph operators. And as all of you will be aware, for line graphs, we have a set of 9 forbidden subgraphs. So the range set or the codomain gets restricted. It's okay if you say that the range is the set of all graphs. Still, we know that some of them are not images, or the mapping is not onto if we take the entire class of graphs as the range. Okay, so why this graph parameter and graph operator? Here we have, I started from domination number, which is a graph parameter, and we have a graph operator motivated from this graph parameter, and that is our gamma graph. Gamma graph of a graph G is denoted by gamma dot G, and the vertex set of gamma dot G is the collection of all gamma sets. Gamma sets means dominating sets of cardinality gamma of G. Okay, so all such sets forms the vertex set of gamma dot G, and 2 vertices are made adjacent to each other if the corresponding gamma sets differs exactly at one position. That is, say, if D1 and D2 are 2 gamma sets of G, then in gamma dot G, D1 and D2 are adjacent if, say, D2 is equal to D1 minus some U union some other V. I can replace U by another vertex V without losing the property of being a dominating set. Okay, so that is the kind of adjacency defined in gamma dot G. Let us look into the example of Peterson graph. Here you have the Peterson graph. I have labeled all the vertices for the sake of simplicity. To construct the gamma graph, first we need to know what is the domination number. In Peterson graph, we do not have universal vertices, so domination number is definitely greater than 1. Again, Peterson graph is 3 regular, so a vertex can dominate at most 4 vertices itself and 3 of its neighbors. So a vertex can dominate at most 4 vertices. So with 2 vertices, you can dominate at most 8 vertices, and Peterson graph has got 10 vertices, so domination number is greater than 2. So if we are able to find a dominating set of cardinality 3, we can conclude that Peterson graph is having domination number 3. And here that is the case. We can find dominating sets of cardinality 3. So now we got the domination number. It is 3. To construct gamma dot G, we need to know all the dominating sets of Peterson graph of cardinality 3. So that is what we need to look into. Again, Peterson graph is having some nice properties. So it is easy to identify the dominating sets. Say, Peterson graph can be viewed as an outer circle C5 and an inner cycle C5 with some special kind of adjacencies. What if I take 3 vertices from the outer cycle? I can dominate the outer cycle. Obviously, I can dominate the outer cycle, but a vertex from an outer cycle can dominate at most 1 vertex from the inner cycle. So if I take all 3 vertices either from the outer cycle or from the inner cycle, then that is not going to dominate the entire graph. So I need to take a 2 + 1 strategy to find a dominating set of Peterson graph. So again, due to symmetry, there is no harm if I take 2 vertices from the outer cycle and 1 vertex from the inner cycle and just repeat the same. So if 2 vertices from the outer cycle means, again, there is a question: 2 adjacent vertices from the outer cycle or 2 non-adjacent vertices from the outer cycle. If I take, say, 1 and 2, then they are adjacent to each other. They can dominate 5 and 3, but it can't dominate 4. So the vertex from the inner cycle must be 9. And you can see that 1, 2, 9 cannot dominate 8 and 10. So if I take 2 adjacent vertices from the outer cycle, then it is not going to give you a dominating set of cardinality 3. Again, if I take 1 vertex from the outer cycle and 1 vertex from the inner cycle, which are adjacent to each other, using similar arguments, you can see that that won't lead to a dominating set. So I have to take 2 non-adjacent vertices from the outer cycle. Say if I take 1 and 3, then the entire outer cycle is dominated, and the vertices 6 and 8 in the inner cycle are also dominated. Now I need to dominate 7, 9, and 10 with 1 vertex. So the only possibility is to take the vertex 7. So if I'm taking 1 and 3, I can be sure that the third vertex is 7. If I take 1 and 4, using similar arguments, you can see that the third vertex is 10. If we proceed like this, that is taking 2 non-adjacent vertices from the outer cycle, then we are forced to fix the third vertex from the inner cycle, and we get 5 dominating sets of cardinality 3. Again, it can be 2 from the inner cycle and 1 from the outer cycle, and that gives another 4 dominating sets of cardinality 3. So these are the 10 vertices. While picking up the dominating sets itself, we have seen that if we take 2 vertices, if we fix 2 vertices, then that automatically fixes the third vertex. So if I can't change the first 2 vertices or any 2 vertices, if I can't change 2 of them, then I can't change the third one also. From that itself, it is clear that there won't be any adjacency in the gamma graph of Peterson graph. So the gamma graph of Peterson graph is nothing but 10K1 or 10 isolated vertices. So from this example itself, we can see that Peterson graph is very much connected, but the gamma graph is totally disconnected. So it can happen that the graph is connected, but the gamma graph is disconnected. Again, the reverse question is also there. If the gamma graph is connected, what about the original graph? So I'll come back to that question later. Now, moving to examples of gamma graphs. Every complete graph is a gamma graph. That is easy. You start with any complete graph. The domination number is 1. So the dominating set will be of cardinality 1. And in that case, the difference between any 2 domination number is the difference in 1 single vertex, right? So every single vertex gives me a dominating set, and every dominating sets are adjacent to each other in the gamma graph. So the gamma graph of Kn is Kn itself. So every complete graph is a gamma graph of Kn itself. We have other examples also. You take any graph which contains P universal vertices. If there is a universal vertex, the domination number is 1. And if there are P universal vertices, then that means the gamma graph of that particular graph as KP, complete graph on P vertices. So complete graphs are all gamma graphs. Again, in the second paper, Professor Sridharan and his student has proved that all trees are gamma graphs and all unicyclic graphs are gamma graphs. They have given a specific construction. You give me a tree T, from that I can construct a graph G such that gamma dot G is going to be the tree T. The similar is the case of unicyclic graphs. So before moving to further details of gamma graphs, let me point out one important thing. The first paper on gamma graphs was published by Professor Sridharan and his student, Dr. Subramanian, in 2008 in Bulletin of Kerala Mathematical Association. The second paper came in 2009, in which they have proved that trees and unicyclic graphs are gamma graphs, which got published in Journal of Combinatorial Mathematics and Combinatorial Computations. And after that, myself and my research supervisor, Professor Ampat Vijaykumar, had written a paper again on the gamma graph of a graph, which got published in AKC, International Journal of Graphs and Combinatorics, in 2010, volume 7. Why I just volume 7? Because in the volume 8 of AKC, International Journal of Graphs and Combinatorics, in the same year, another paper got published, a note on gamma graphs due to Connelly, Hedeknimi, and Hudson. They have introduced a similar graph operator and they have named it as gamma graph itself, but it is different from the one introduced by Professor Sridharan. The only change is that the vertex set again corresponds to the dominating sets or the gamma sets of the original graph. Two vertices are adjacent if the corresponding dominating sets differ at exactly one position. Up to that, it is the same. And there is one additional condition that these two vertices must be adjacent to each other. Okay, so there lies the difference. The difference is that of one vertex, and those two vertices are adjacent to each other. When they wrote this paper, I think they have not seen these two papers due to Professor Sridharan and one paper published by ourselves. But maybe after communicating the paper, as you all know, there is a lag in publication. By the time it got accepted for publication and it came out in the AKC journal itself, they noticed that we already have some other graph with the same name. So this part they have added at the end of the paper, mentioning that there are 3 papers on gamma graphs, the same name, but the concept is different from that of ours. So beware, there are papers on gamma graphs based on Professor Sridharan's definition and based on Professor Hedeknimi's definition. So you should not get confused when browsing through internet for papers on gamma graphs. Again, a third paper due to Professor, of course, third paper is ours. This is 4th paper on gamma graphs. A 4th paper on induced subgraphs of gamma graphs got published in Discrete Mathematics, Algorithms and Applications in 2013 due to Professor Sridharan, his student Amruta, and yes, Rao. And in that paper, they have proved that every induced subgraph of a gamma graph is again a gamma graph. That means gamma graphs have vertex hereditary property. If a class has got vertex hereditary property, there is a chance that we can characterize those graphs using forbidden subgraphs. We'll come to that. In the same paper, they have proved that if H is equal to gamma dot G, that is H is the gamma graph of a graph G, then we can find a sequence of non-isomorphic graphs, a class of an infinite class of non-isomorphic graphs, all of whose gamma graph is H. Say, in the case of line graph operator, we have seen that such a thing happens only for triangle and K13, both of which have K3 as the line graph. Except that pair, if we have LG isomorphic to LH, then G isomorphic to H. So whenever we consider an operator, this is an interesting question. That is, if say phi is the operator, then phi G isomorphic to phi H. Does that mean that G is isomorphic to H? In the case of gamma graphs, we have a negative answer. In fact, If H is a gamma graph, we can have an infinite collection of graphs, all of which have their gamma graph as H. So before going to forbidden subgraphs, I need this definition of Cartesian product of graphs. So Cartesian product of two graphs, G with vertex at V1 and edge at E1, and H with vertex at V2 and edge at E2, denoted by G box H, is a graph having vertex at ordered pairs V1, V2, where V1 is a vertex from G and V2 is a vertex from H. And two vertices are adjacent to each other. Say two vertices V1, V2 and V1 dash V2 dash are adjacent to each other. If either V1, V1 dash is an edge in G and V2 is equal to V2 dash, or V1 is equal to V1 dash and V2, V2 dash is an edge in H. Here you have an example. This is our first graph G and this is H. You can see that there are two copies of the first graph G, that is triangle here, and three copies of the second graph. It is always like that. If you take G box H, you get H copies or H layers of G and order of G layers of H. We can always partition the H set like that. Here you have one more example. This is going to be the Cartesian product of these two graphs. The first graph, you have 4 copies drawn vertically. And for the second graph, you have 5 copies drawn horizontally. And their union gives you the Cartesian product of G and H. So that is the concept of Cartesian product of two graphs. Coming to forbidden subgraphs, as evident from Professor Sridharan's paper, we can be sure that there are forbidden subgraphs for gamma graphs, and there is all chance that we can characterize gamma graphs using their forbidden subgraphs. In their first paper itself, they have given one forbidden subgraph of gamma graphs and left it as an open problem to identify all forbidden subgraphs of gamma graphs. So what is a forbidden subgraph? A graph H is forbidden for a property P if G satisfies P if and only if H is not an induced subgraph of G. G is having property P, then H is absent. If H is absent, we have property P. If such a condition is satisfied, we say that H is a forbidden graph for the property P. Again, as I mentioned earlier, for line graphs, we have 9 forbidden subgraphs which characterizes them. If they are not present, then we can be sure that it is a line graph. And if any one of them is present, we can be sure that the graph is not a line graph. That is the idea of forbidden subgraph characterization. So again, if a graph is forbidden, obviously any supergraph of it will be forbidden because that contains this smaller graph H as an induced subgraph. So when we talk about forbidden subgraphs, we are interested only on the minimal ones. A subgraph H is minimal forbidden if none of its subgraphs are forbidden for the property which is under consideration. So whenever we say forbidden, we definitely mean minimal forbidden. Now, when we try to identify the forbidden subgraphs of gamma graphs, the first thing that I would like to bring to your notice is that we need to consider only connected graphs. Because if say H1 and H2 are two disconnected graphs, if H1 equal to gamma dot G1 and H2 equal to gamma dot G2, then G1 union G2 union K2 is nothing but the Cartesian product of H1, H2 and K2. In fact, before that we have proved a lemma. If you take G1 union G2, then the gamma graph of G1 union G2 is Cartesian product of gamma graphs of G1 and G2. Here we are taking one K2 also to ensure that the resultant graph contains two disjoint copies of H1 and H2. If either H1 or H2 is forbidden, then obviously this also becomes a forbidden structure. If both of them are not forbidden, then this is also not forbidden. So from that, we can be sure that a minimal forbidden subgraph will be always connected. So here you have all forbidden subgraphs on 5 vertices. In fact, the second graph was identified as a forbidden subgraph of gamma graphs in the first paper itself, in the fourth paper due to Professor Sridharan itself. And he had talked about that during his talk in 2008 at my conference also. And we have given all forbidden subgraphs on 5 vertices. Of course, there are more forbidden subgraphs on 6, 7, 8, 9 vertices. This is not a characterization, but these are the only forbidden subgraphs on 5 vertices. So I will explain just one of them. The first one is K32. K32 is forbidden. The proof of K32 same as K23, okay, is forbidden is quite simple. Say if it is K32, then there are 3 vertices in the first partate and 2 vertices in the second partate. Corresponding to that, we have 5 dominating sets in the original graph. Let those dominating sets be U1, U2, U3 and V1, V2. And since they induce K32, I can be sure that every Ui is adjacent to Vi in gamma dot G. So let us start with U1. Say U1 equal to U1, U2, etc. UK, where K is the domination number of G. So I have taken a dominating set corresponding to the vertex U1. Now U1 and V1 are adjacent. So they can differ at most in one position. So without loss of generality, I can assume that they differ in the first position. So V1 must be of the form V1, U2, etc. UK. And now V2 is also adjacent to U1, but not to V1. So U1 and V2 also differs at first position, but that position is not U1. If instead of U1, we are having some other vertex in V2, then V1 and V2 also will be adjacent. So that is some other position, and without loss of generality, we can assume that the difference is in the second position. So V2 will be of the form U1, V2, etc. UK. Only the second vertex U2 is replaced by V2. But now we must have U2 adjacent to both V1 and V2. V1 is like V1, U2, etc. UK, and V2 is like U1, V2, U3, etc. UK. So U2 must differ exactly at one position from V1 and V2, means the only possible choice is you take V1, V2 and take all other UIs, U3, etc. UK. So the V1 and U2 differs at U2. U2 is replaced by V2. And when we take V2 and U2, they differ in the first position. U1 is replaced by V1. And this is the only possible choice for a vertex which is adjacent to both V1 and V2. But we need one more vertex U3 of the same property, which obviously do not exist. So K32 is a forbidden subgraph for the class of all gamma graphs. This is quite simple. And it is not that difficult to prove that those 4 graphs are the only forbidden subgraphs on 5 vertices. Now, recently, some of my students did as a part of their UG project work, they tried to identify all forbidden subgraphs on 6 vertices. Thanks to Ashisha and Teresa, they have done this work and they have identified that these 4 graphs are the only forbidden subgraphs on 6 vertices. The things were not that easy when compared to identifying forbidden subgraphs on 5 vertices, because there are plenty of graphs on 6 vertices, and their strategy, yes, I will show the idea of the proof. This was basically their idea. There are 156 graphs on 6 vertices. When we are looking for minimal forbidden subgraphs, we need only consider connected graphs. So we need not consider all those 156 graphs. We have 112 connected graphs on 6 vertices. Among that, the complete graph is always a gamma graph. So we need not consider that one. Again, Professor Sridharan had proved that all trees and unicyclic graphs are gamma graphs. So they are not forbidden subgraphs of gamma graphs. So we can eliminate them also. After eliminating all unicyclic graphs and trees, 92 graphs were left. And among them, we already have 4 forbidden subgraphs on 5 vertices. If that graph is present as an induced subgraph, then this graph on 6 vertex won't be a minimal forbidden subgraphs. So we can eliminate all super graphs of the 4 minimal forbidden subgraphs on 5 vertices. So they have eliminated them, and then they were left with 52 graphs. And in again, our paper, which was published in AKCE International Journal in 2010, we have proved that Cartesian product of 2 gamma graphs is again a gamma graph of some graph. So among these graphs on 6 vertices, there are 2 Cartesian products. So Cartesian product, again, connected restriction is also there. So there are only 2 possible choices. You take P3 Cartesian product K2 or K3 Cartesian product K2. So those 2 graphs can also be eliminated while looking for forbidden subgraphs. So now we are left with 50 graphs. For that 50 graphs, out of that 50 graphs, 46 graphs admits realizations that you input graph and the program will give you an output, which is a graph whose gamma graph is the graph which we have inputted. So you give H, the program will give you a G such that gamma dot G is equal to H. This is true for 46 graphs. And we were left with 4 graphs. These were precisely those 4 graphs. And logically, we could prove that there does not with the help of computer program, but using logical arguments, we could prove that these 4 graphs are not gamma graphs of any graphs, or even they cannot be present as an induced subgraph of gamma graph of any graph. So that was it. Then coming to closure property with respect to graph products. If you take 2 graphs that are regarding Cartesian product, I have already mentioned that you give me 2 graphs which are gamma graphs and take the Cartesian product, then that Cartesian product is again the gamma graph of some graph. So for the class of Cartesian product, there is closure property for the subclass of gamma graphs. Okay, so that's it. But such a result is not true for tensor products and strong products. In the case of tensor products, we have K5 and K2 as gamma graphs, but K5 tensor product K2 is not a gamma graph. Again, K3 and P2 are gamma graphs, but K3 strong product K2 is not a gamma graph. So for the class of tensor products and strong products, the closure property is not there. Another way of looking at it is to consider the gamma graphs of special classes of graphs. So here we take an example of that of co-graphs. Co-graphs are complement reducible graphs. That is the graphs which reduces to isolated vertices when we take complements within components. So C4 is an example. When you take complement, you get 2K2. And again, you take complement within components, what you get is 4K1, which are isolated vertices. So C4 is a co-graph. But if you start with C5 and take complement, what you get is C5 itself. So again, you take complement, you get C5 itself, like that. Okay, so self-complementary graphs are not co-graphs. Okay, you start with house, the complement is P5. Again, you take the complement, you get back house. So if there is only one component in the complement, that is complement is connected, then G complement gives me back G itself. So a graph, to be a co-graph, the complement of it must be disconnected. And co-graphs have many interesting properties. They admit forbidden subgraph characterization. They are P4 free graphs. And they can be constructed from K1 either using the operations of union and complementation or using the operations of union and join. And their diameter is at most 2. Of course, the converse is not true. Now, coming to gamma graphs of a co-graph, we have characterized the graphs which are gamma graphs of a co-graph. The proof is by induction. Since there is time constraint, I am not going into the details of the proof. Again, the diameter of a co-graph is less than or equal to 2. And we have proved that the diameter of the gamma graph is also less than or equal to 2, provided the starting graph is connected. If the starting graph is disconnected, the diameter may increase. Here you have an example. If G is equal to C4 union K2, then you take the gamma graph, the diameter is 3. Now, another direction is impact of gamma graphs on various graph parameters. You can see that click number, independence number, chromatic number, all these parameters do not have any direct relation with gamma graph. It can vary arbitrarily. And there are some variations of gamma graphs also. Despite considering usual dominating set, if you take total dominating set, what you get is gamma total graph with the same definition. You take independent dominating set, you get gamma independent graph, and likewise. So such variations are there in the history. So here are some open problems. Obviously,
your time is over. Please.
Okay. Yeah, I have concluded. These are the list of open problems.
Within 2 minutes.
Yes, sir. So these are the list of open problems. Characterization problem is open. Identifying forbidden subgraphs of vertices greater than or equal to 7 is open. And recognition of gamma graphs, that if you are given a gamma graph, can you say, if you are given a graph, can you say that it is the gamma graph of some graph or not? And identifying classes of gamma graphs, say trees, unicyclic graphs are all gamma graphs. Like that, does there exist any other class? And find gamma graphs of particular classes of graphs. Again, the dynamic problems are also interesting. I have already told that the click graph of, the gamma graph of a complete graph is itself. Such graphs are called fixed. So identify gamma fixed graph, look for gamma convergent graphs, look for gamma divergent graphs, look for gamma periodic graph. All sorts of such dynamic questions are open. Again, closure property and impact on graph parameters. So there are plenty of opportunities in this particular topic, gamma graph. So these are my major references. There are only a handful of papers published in gamma graphs. So that's it. Thank you.
So thank you, Dr. Aparna, for a very informative invited talk. So if is there any comments or questions, please. Participants are requested if they have
Aparna,
anything in
Yes,
chat box or
as usual, it was an excellent presentation.
Thank you, sir.
This gamma graph is same as the intersection graph of the dominating sets, right?
Not exactly, sir. In the case of intersection graph, what they say is that they must intersect. Here, they must intersect on gamma g minus 1. The intersection must contain gamma g minus 1 entries. So that is the difference.
Oh, please tell that again.
Intersection graph means you take vertices at the gamma sets and two vertices are made adjacent if the corresponding gamma sets intersect. Only that much is there.
Okay.
They intersect. But when coming to gamma graphs, this intersection must contain gamma of g minus 1 vertices. So there lies the difference.
Well,
Of course,
okay, that means
graph, we can say super graph of this.
it is only one vertex less, right?
Sorry, sir.
The intersection cardinality will be one less.
Yeah, exactly, sir. It will be gamma.
Okay. Aparna, you see, the neighborhood number and neighborhood sets are the generalizations of dominating sets.
Yes, sir.
So there is some study with reference to neighborhood intersection sets. In fact, I and Joseph Strait have done some work also.
Yeah.
I'll send you that paper. I would like you to respond. And I am interested if enumeration of gamma graphs for all graph structures have been made.
Yes, sir. That is an interesting question. Again, an open problem. Enumerating.
Okay, thank you. Yeah,
okay.
Thank you, madam.
One participant, Swan Mane, has raised a hand. So please unmute yourself and ask a question.
Sir,
I'm sorry.
properties of gamma graphs are studied or not for some classes?
I'm sorry. Please repeat it.
Whether spectral properties of some classes of gamma graphs are studied or not?
No.
want to
It's
know.
open. Study of
Okay.
parameters of gamma dot g is open. Only on independence number and click number we have some results, and chromatic number. All other graph parameters, study of all other graph parameters, including spectrum, is open for gamma graph.
Thank you, ma'am.
Okay. So I have a question. So whenever talk about the intersection graph, the K intersection graph is there, right? So The intersection should contain exactly the k in it, k common
Yeah.
cases.
Yeah.
So
Here we
this
can
is
say
one
that
of the
this is
intersection
gamma
graph.
G minus 1 intersection graph.
Yeah, exactly. So this is one of the gamma G
The
minus
thing is
1.
that this for k independent means that k is fixed. Once we consider k intersection graph, that k is fixed. Here gamma of G minus 1 is not fixed. That depends upon the graph G.
Exactly.
So we can't say that this is a kind of k intersection graph, but yeah, it is somewhat related to it.
Okay. One more question about the forbidden subgraphs.
Yeah.
So you have considered, so finding all the forbidden subgraphs is not very difficult maybe, right? Because you have 3-4 graphs for 5 vertices and again 4 graphs for 6 vertices. So finding all these things do you think it is possible?
Yeah, that's like a game, I must say. The thing is that to prove that a graph is forbidden, we need some work. But to prove that a graph is not forbidden, it is easy. You can simply write a program, input that graph, and you get the output. But to prove that it is forbidden, we need some theoretical work in it. Otherwise, that's not a tough thing. But when moving to a higher order, it becomes difficult.
Yeah, anyhow, when we talk about forbidden subgraph, we need to find all the collection of all the forbidden subgraph, right? For a particular property.
What I expect is that collection is infinite in the case of gamma graphs.
Yeah, so that is what I am also expecting. So it is an infinite graph. Then it is not possible to find out, right?
To find
the collection of all forbidden subgraphs.
It's not that easy, sir. You can definitely try. I tried to find at least infinite classes of forbidden subgraphs, which is not coming out that easy. You can just try, and if you get something positive, I'll be very much interested.
Yeah, because in terms of planar, it is only K3 and K5 are the forbidden subgraphs. So whenever it's
K3 and K5 and their homeomorphic operands.
Yes, exactly. So whenever talking about the higher order of genus, we have for genus 1 itself, we have about 103 graphs of forbidden subgraphs.
Yeah.
Okay, so the class is finite, so they have able to find out all the forbidden subgraphs. But for the gamma graph, I think it is maybe an infinite class of graphs. And that way,
what I expect, say again, if we consider perfect graphs, all odd cycles and its complements are forbidden. That is an infinite collection, but still it's easy to check, right? But I don't expect such a result, even such a result for gamma graphs. This collection may vary without having a relation to each other. So I don't expect to get a good characterization using forbidden subgraphs. That is what I was trying, but I don't think it will come out. But if it comes out, well and good.
Thank you so much.
My question is, given a class of graph, can you find some graph for which this is forbidden? I am coming to the converse problem. Given a graph G, can you find some other graph H for which this G is forbidden?
That is an open question, sir. We can definitely find, but that is an open question.
But my question is, does it possible for at least some special classes of graph? For example, complete.
It is possible, sir. It is possible. Say in the case of complete graphs, complete graph won't be a gamma graph if there is no universal vertex in the original graph. Like that, something can be done.
Excuse me.
Yes, sir.
I think the Tamil Selvan's question is different. I give you a collection of subgraphs. I want to construct graphs for which these graphs are forbidden. Am I right, Tamil Selvam?
Yes, yes.
It is not with respect to gamma graph. I think its question is general.
No, it is not possible.
No, it is with respect to gamma graph.
Oh, okay.
1 minute.
It is with respect to gamma graph only, not in general.
1 minute.
Professor Sridharan, please.
Yes, it is not possible to do that. If the graph is gamma graph, then it is not a forbidden graph. If the graph is not a gamma graph,
okay.
Graph is a gamma graph.
So I should not take initially the gamma graph.
Just to find out, is it a gamma graph or not a gamma graph? That's all.
Okay, so the problem is ultimately rely upon whether it is a gamma graph or not.
If it is not a gamma graph, we have to find out the minimal gamma graph in that.
Okay, fine.
It may contain K23. It is forbidden.
Yes.
Therefore, we have to reduce the size of that down for gamma graph.
Fine.
So whether if a G is given, find out whether it is a gamma graph or not. If it is a gamma graph, it is not a forbidden graph. If it is not a gamma graph, then it contains a forbidden subgraph.
For sure.
We have to find out the minimum one.
Okay, fine.
Okay, in that case, how do you know that a given graph is a gamma graph?
That recognition problem is open, sir. To
Open.
identify whether a given graph is a gamma graph or not is still open. We
Okay.
know that we have some set of forbidden subgraphs, but not all.
Okay, do you know the gamma graph of Srikanta graph?
That I haven't tried, sir.
Okay, because I am converging to Srikanta graph everywhere, because there is a very beautiful book on Peterson graph. So sometime we may have a book on Srikanta graph where all the nice properties of Srikanta graphs are listed. Collaborations are welcome.
Okay. It won't be difficult to
So
find
even
that.
the automorphism group of Srikanta graph is not as easy as Peter mentioned yesterday. So I don't know whether finding the gamma graph of Srikanta graph will be easy.
I'll definitely find and let you know, sir. It won't be difficult, but because it's a finite graph, we can easily find.
I see.
Just 1 minute.
There are no other questions. I will have one more question. Given a graph G, you talked about dominating sets having property P, right?
Hmm.
How about the converse problem in the sense that I have a dominating set with property P. Can you construct a graph G with property P having this as a dominating set? Just like given a graph G.
The properties for the set, right? So
Given
the
let me complete. Given a graph G, I can construct a graph with property P, which has this given graph G with property P as the median or anti-median. Like that, it is possible.
Sir, if the property is connectedness, okay, it's possible, sir. You fix a property. If there is a set having that property, then we can definitely construct a graph from that, so that this set is dominating. We can do that. You can take Corona operator, so that this original starting graph becomes the dominating set. So it is always possible. I heard someone else also. I heard a female voice.
You are hearing my voice.
Yeah, yeah, ma'am.
Aparna, thank you for your nice talk.
Thank you,
Just, I have heard the name of gamma, but gamma graph I am hearing first time. And I would like to.
Then you were absent for 2018 ATMA conference, ma'am.
No, madam. I was very well. I came to attend 2008 ATMA conference, but mentally I may not be there, you know.
Yeah, that's it.
Because Dr. Acharya was already very serious and all other thing, but he made me, he said, you go and attend the conference. I did come for the conference, and I think last day was the workshop when I reached. And but anyway, I will see to that one. Okay, that's some input, if not for graphs, but in topic in which I am more interested, that I will try. Okay.
Time graph.
Thank you. Thank you.
Yeah, thank you.
If there are no questions and comments, then we conclude this talk. And with my remarks that Dr. Aparna, you have covered all the aspects for a new class of graphs like forbiddenness, enumeration, and closure property. So thank you very much for such a nice and informative talk. And I would like to mention, because it was not written in this biodata of Dr. Aparna, but she has mentioned that we have experienced the essence of Dr. A. Vijay Kumar, because she is the student of Dr. A. Vijay Kumar. So that is the thing. With this remarks, I'm very much thankful to organizing committee for this ICDM21 to provide the platform and to witness such informative talks. Thank you, one and all.
Thank you, Professor Samir Vaidya. And once again, thank you to the organizing committee and Thamizselvan sir for giving me this opportunity. And I would like to add, whatever I have, I owe to Professor Ampad Vijay Kumar. So thank you very much.
Thank you.
Ranjini, please.
Thank you, ma'am. Thank you for this wonderful session. I also thank Professor Dr. S.K. Vaidya who initiated the session. So shall we begin the next session?
At what time we are supposed to? We are supposed
11,
to be at
sir.
what time?
11, sir.
We can start.
Okay, sir. Thank you, sir.
I
To begin with,
Professor Venkatesh Raman has already joined.
Yes, sir. He
yes,
joined.
sir.
Did you make him as co-host?
Yes, sir.
Some Pantingla.
Sir, he is already as a co-host.
Okay.
Oh, he's already there.
Fine. Professor Venkatesh Raman. Good morning.
Venkatesh, good morning.
Good morning, Venkatesh.
Good morning. Good morning.
Good morning to all, Dr. Tamil Selvam, everyone.
Ranjani, please.
Yes, sir. To begin with the next session, I am very much happy, proud, and privileged to welcome our beloved Professor Dr. S. Somasundaram, who is very famous for his timely sense of humor and his unique method of teaching via pictorials, which always takes up the corner of the board. Now, I request our renowned Professor Dr. S. Somasundaram to introduce the speaker to us. Please, sir.
First of all, I start by thanking the organizers for having given me this nice opportunity to introduce, to give a brief introduction of about my friend, Dr. Venkatesh Raman. Dr. Venkatesh Raman, in fact, he had his school also, I suppose. Surely I know he had his undergraduate graduation in Tirunelveli, particularly in St. Xavier's College, Tirunelveli. And then he moved on to IIT Kanpur for his master's in mathematics. Here I would like to have give a personal touch to. I happen to be 2 years senior to him, both at St. Xavier's and also in IIT Kanpur. I joined for my PhD and he joined for his MSc in IIT Kanpur. Then Professor Dr. Venkatesh Raman moved to University of Waterloo, Ontario, Canada for his M-Math program and subsequently for PhD also. I think he was in the department associated with computer science. Exactly, I'm sorry. Maybe Venkatesh Raman himself might be able to tell me the discipline of the department. He then joined Math Science. From there, then he joined Math Science Chennai. Technically, he's a faculty of, now he's a professor there and he's technically a faculty of the computer science. But then based on my brief stay at Math Science, I could hardly find any line of divide between two disciplines there, as has to be in any ideal institution. Dr. Venkatesh Raman has published widely and he has guided a good number of PhD scholars. He is a scholar true to the spirit of the word, true to the word. He also he has apart from academics too. Mute someone. Kindly mute someone. So apart from the academics, he has a wide reading with the social concern. I should stress upon that. So hence, and he continues to be my friend always. I suppose I'm very fortunate to have him as my friend, and I'm very fortunate today. As I repeat, I'm very fortunate to give a brief introduction. This is a very brief introduction. If you allow me to talk, I can take even at least half an hour on him. Sorry, he has to lecture. So we are fortunate to hear him lecture on fast Fourier transform and graph coloring algorithms. On behalf of all of you, I extend a warm welcome to him. I invite him to speak. As people used to say, sir, the dash is yours. I would say the screen is yours now. Please.
Thank you. Thank you very much for the nice introduction. And I thank the organizers for inviting me. I hope you can see my screen and listen to me well.
Yes. Yes.
Yeah. Okay, good.
Yeah.
So, since this conference is preceded by a workshop on some algebra related things. So when I was thinking of what talk to give here, I tried to connect it with some algebraic stuff. So that's the title, First Fourier Transform and Graph Coloring Algorithms. And so essentially there will be two aspects to this talk. I'll talk about fast Fourier transform. It dates back to Fourier and Gauss and so on, but the modern version of it in an algorithmic sense, it's a very nice tool. That's what I hope to convey in the first part of the talk. And then this tool has a lot of algorithmic applications. So I'm going to touch upon one in the context of good algorithm for finding the chromatic number of a graph. Okay. So the starting point of our story is this problem. You have two polynomials, univariate polynomials with complex coefficients, let's say, of degree at most n, and you want to multiply them. Okay, just want to compute the product of these two polynomials. Okay, this is standard. You've all learned it in high school. We know how to do it. So the standard way to do this, you compute all the coefficients. So for example, the constant term coefficient would be P0, Q0. The X term coefficient in the product would be P0, Q1 plus P1, Q0, and so on and so forth. So the number of multiplications you do is 1 plus 2 plus 3, because 3 terms, to get an X square coefficient in the product, you do 3 multiplications, and so on and so forth. So it will be 1 plus 2 plus 3 up to some 2n. So it's an n square algorithm. Okay, the number of multiplications. So you're computing something like 2n terms, so 2n minus 1 terms. And each term computation takes about order n. So overall, it's an n square algorithm. And the goal of fast Fourier transform is to compute this much faster, in particular, using an n log n algorithm. Okay, so that is what I hope to convey in the first part of the talk, to how to multiply two polynomials of degree n using n log n time. Okay, and let's look at the polynomials in another representation, which I'm going to call it as point value representation. Notice that each of these polynomials, they have n coefficients. So they can be uniquely represented if I know the value of these polynomials on n distinct values, n distinct terms, right? N distinct points. If I know the value of these polynomials, I can compute the coefficients. And the reason, you have a system of equations on n unknowns, and this matrix you have is basically this van der Maan matrix, which is invertible. So you can, compute the inverse, multiply by the right-hand side, and you get the coefficient. So this is the representation. This is one other representation of these two polynomials, or any polynomial of degree at most n. Now notice that if I know these two polynomials, the value of these polynomials on 2n distinct values, or 2n minus 1 is good enough, I think, then the product is easy to compute, because in this representation, all I need to know is the value of this product polynomial on these 2n distinct points. And that is easy because you just have to do point-wise multiplication. If I know px on 2n points, qx on 2n points, the same 2n points, then computing this product is just do point-wise multiplication. Right? So that's actually linear time. Recall that in the standard coefficient representation, we saw that it actually takes n square time, whereas here it's linear time. But not always you are given the polynomial in this form. So one way to do it is, if you are given in the coefficient form, you fix your 2n points, evaluate these polynomials on these 2n points, and then do this pointwise multiplication. And then maybe you have to transform back to the coefficient form. But then transforming from coefficient representation to point value representation can take n square time. So we lost all the advantage of this product being computable in linear time in this representation if I have to go from coefficient representation. Because computing a polynomial of degree n in one point is going to take you some n time. Okay, So we have one representation where multiplying two polynomials takes n squared time, and another representation where actually multiplying two polynomials take linear time. Now we want to see, is there somewhere in between, right? Now the interesting thing to notice is that in this point value representation, it is enough to compute these polynomials on any n distinct values. So the key idea is that any distinct points suffice. So the question we want to ask is, are there some n distinct points where you can evaluate the polynomials faster than n squared time? Okay. So in particular, if you can evaluate a polynomial on some n different points in n log n time, then we have more or less achieved at least a part of the goal, because from the coefficient representation, you can go to the point value representation in n log n time, do product multiplication, pointwise multiplication. At least you have the evaluated the product polynomial on the 2n points. So you need to worry about how to go back to coefficient representation. We'll worry about that later. And it turns out, yes, you can find some n distinct points where you can evaluate the polynomials faster. And that brings us to this notion of Fourier transform. And here it is, right? So given this polynomial Px, let me break it up into two polynomials. One which contains the odd degree coefficients, the other contains the even degree coefficients. So it's P0 plus P2x plus this is I call PE of x, and PO of x is this polynomial. Then we can write Px as PE of x square plus x times PO of x square. Okay, this is very easy to see, some simple manipulation. But notice that these two polynomials have half the degree. The original degree was n. This has roughly n by 2 degree. Okay. Now, people who are familiar with n log n in algorithm analysis, where this n log n comes up, right? It is usually by this divide and conquer. You solve two problems of half the size and put things together in linear time. You get an n log n algorithm, and that's the direction we are getting into. So I have these two polynomials of half the degree each than what we started off with. Now I want to evaluate these two polynomials on n points, because that's what will give me P of x. So here is, okay, for all the talk, I'm going to assume n is the power of 2. It just simplifies a lot of calculations, because you don't have to worry about n by 2 or n by 4 being not an integer. So here is the first idea. Remember, our goal is to choose any n points. Okay, so what we are going to do is choose n by 2 distinct points and then take their negations to the other set of n by 2 points. Okay, so I pick some n by 2 distinct points and take their negations as the other n by 2 distinct points, and I have totally n distinct points. Now notice that the squares, when you square them, you don't have n points, you have only n by 2 points. So now if you come back to this polynomial, this equation P of x is PE of x square plus x times P0 of x square. You are evaluating these polynomials which are half the degree on x square, but x square there are only n by 2 distinct points. So it looks like you are ready for a recursive algorithm. Evaluate P0 on some n by 2 distinct points, PE on n by 2 distinct points, put things together, and you get your Px. Okay, so this would look like we have a recursive algorithm which has a recurrence relation, two polynomials of half the degree evaluated at half the number of points. And then we spend linear time to compute this P of x. Remember, there is an x sitting here where you need to multiply. This will be plus or minus depending on the points, which solves to n log n.
Anyway, there is one only after that.
Okay, but they are not done yet, because there is one little problem, which is that initially we are evaluating this polynomial on points where half of them are distinct, the other half is the negation of the other. If I have to apply this idea recursively or inductively on the smaller polynomials, the points where I'm evaluating should also be of this type, right? Half of them are positive, half of them are negations of them. Well, are they of this type? Well, we don't know. We didn't carefully choose them. Especially, you're squaring them. How can you get square of some numbers to be negation of some other numbers? How can you have squares to be negative? Right? So one catch are the points to be evaluated the same type of the recursive subproblems may not be. And it turns out if you choose the endpoints as complex nth roots of unity, things work out very nicely. Simply because, first of all, those endpoints are, half of them are positive, half of them are negative of the positive guys. And if you square them, they form complex n/2th roots of unity. So now this gives you a nice setup for a recursive algorithm. So in other words, we are evaluating this P on n complex nth roots of unity. And the way we evaluate it, by recursively evaluating PE and PO on their square, which is complex n/2th roots of unity, and the polynomials are of the degree. And then you spend linear time to put things together. So we have this recurrence, which gives you n log n. Okay. So if you missed what I said, essentially here is a summary here, right? So you want to move from coefficient representation to point value representation of polynomials. One way to do it is just efficiently do it is to evaluate them on n complex nth roots of unity. They have so many nice properties that they lend themselves to a recursive algorithm, giving rise to an n log n algorithm to evaluate. Remember, the naive algorithm takes n square, and this takes n log n. It turns out the interpolation, the inverse of this is also very easy. What is the inverse thing? Because if I compute px and qx in the same way and then do a pointwise multiplication, what do I have? I have the product polynomial on evaluated on this n or 2n, okay, asymptotically they all get observed, on this 2nth roots of unity. Now, if I want to go to coefficient representation, you have to invert some sort of a van der Waals matrix, but the matrix inversion can be done efficiently here simply because these points are roots of unity. Okay, so you can do the interpolation also in n log n. Okay. So to summarize what I said, you're given two polynomials in this coefficient representation. Evaluate them on complex nth roots of unity. I mean, when I meant n here, actually 2n, because for the product polynomial, you need 2n different values. And this is the discrete Fourier transform. What is this Fourier transform? It takes this complex n-dimensional vector, this coefficient vector, into another n-dimensional vector, which is this polynomial evaluated at this complex nth roots of unity. Do the same for qx, and then compute px, qx pointwise in linear time, and then interpolate it back to get the product representation, coefficient representation of the product. Okay, so I have told you, hopefully, almost complete details on how to compute the product of two polynomials of degree n each in n log n time instead of the naive n square time. Okay, this is something you can actually do the whole thing in a first course on algorithms. All they need to know is the properties of nth roots of unity. In fact, you can even do it in a complex analysis course, because who would have thought that something esoteric like nth roots of unity will have such a nice application in algorithms, right? I find it a very interesting tool. Okay. Now, let's see some. So again, one other thing, when we actually do these implementations, these complex numbers give rise to a lot of floating point arithmetic, all kinds of issues. But instead, you can actually work with the large finite ring that has complex roots of unity. Right? This is also another nice application of, modern algebra, where you talk about rings and roots of unity in a ring and so on. Right? Okay, good. So now I'll give you some applications. I'm going to talk about this chromatic number application. But before that, here is a simple warm-up application. Let's say you want to multiply two n-digit numbers, which you have learned in high school, right? You have this, suppose I give you two 10-digit numbers, we know how to multiply. We learned this algorithm in school where you multiply the entire first one with the last digit, and then do a carry, the next first one with the next digit, and so on and so forth. If you do your careful calculations, you are actually doing n square multiplications, right? If it's an n-digit number, then the entire first number is multiplied by this one digit, which costs you n multiplications. And then you do it with the second digit, third digit, and so on. That's overall an n square multiplication. This is the basic arithmetic multiplication which you learn in high school. Now notice that multiplying two n-digit numbers is essentially multiplying two polynomials of degree n-1, because each, what is 535? 535 is 5 into 10 square plus 3 into 10 plus 5, right? It's a quadratic polynomial evaluated at 10 with coefficients 5, 3, 5, right? So you can write any n-digit number as a polynomial evaluated at 10, because you're talking about decimal. If it's binary, you will evaluate it at 2, right? So multiplying two n-digit numbers boils down to multiplying two polynomials of degree n. You multiply them and evaluate it at 10, and that gives you this product number. But I just told you that you can multiply two polynomials not in n square time, but in n log n time. So you can do this product of two integers in n log n time, because you just have to write them as polynomial, apply the FFT algorithm, multiply, and evaluate it at 10. This is a big deal because, multiplication of two numbers is every software, every program will be doing day in and day out thousands of times. And so somehow an improvement like this is great because it has a big impact. It's a very basic arithmetic step which you are improving from n squared to n log n, right? You all know log n grows very, very slowly compared to n. So n into n and n into log n, there is a big speed up, especially for large values of n. And this is okay. So it's a very powerful application of this fast Fourier transform. I will mention one little caveat here. When I say time here, I'm talking about in the FFT context, multiplying complex numbers, possibly of large complex numbers. So it may not be a fair comparison with an n square time high school multiplication where you're just multiplying one digits. But this has been a strong research area to bring down this time n log n as actually n log n bit operations. There's been a lot of work starting from 2000, in fact 19 something all the way to 2019. Actually here time means you can even say it's bit operations. So this requires a lot more than what I described you in the first few slides. Okay, so if there are any questions, feel free to ask. You don't have to wait till the end. So what I have told you is how to multiply two polynomials of degree n in n log n time using fast Fourier transform, which has uses all the properties of complex roots of unity. And one simple application is multiplying two n-digit integers. Now let me actually get to the chromatic number problem. Okay, so this has a lot of applications. I just picked this because of this graph theory interest here. So you all know what a chromatic number problem is. Given an undirected graph and n vertices, you want to color the vertices with the minimum number of colors so that endpoints of every edge gets distinct colors. Okay, the decision version of this problem will be is the chromatic number at most k. Again, by now I'm sure most of you know this term NP hard, which means it's one of the hard problems. You don't expect an algorithm which is polynomial in n and k taking time. For k equal to 2, it's easy checking whether a graph is bipartite, but anything beyond 2, it's a hard problem. So now what I'm interested in is, okay, it's a hard problem, but I want an exact algorithm for this problem. Okay? A brute force, exponential. I understand that I have to live with an exponential algorithm because it's a hard problem, but can you give a good exponential algorithm? Okay, that's our question. So a naive brute force algorithm to check whether a graph has chromatic number at most k would be as follows. Try all possible values, right? For every vertex, give any of one of the k colors and check whether the coloring, what you have is a proper coloring. That's an easy step. So the number of possibilities you have to run through is k power n. Okay. So k can be very large. So the question is, can you actually bring it down to something better exponential? Maybe 4 power n, 3 power n, 2 power n. Even though if the chromatic number is 100, this algorithm says 100 power n. No, I don't like that. I want something much better exponential algorithm. Okay. First, I'll give you a simple, faster algorithm than k power n using standard dynamic programming. This is also a very, very good college level exercise on dynamic programming, slightly non-trivial compared to the standard dynamic programming examples they do in first course. So what we'll do is we'll compute the chromatic number in a bottom-up fashion, starting from small subgraphs. So you have this huge graph. I want to know its chromatic number. So we will find the chromatic number of all small pieces of this graph, small subgraphs, and then build up to eventually to the big graph. Okay, that's the way dynamic programming works. So the starting point would be all graphs of size 1, size 2, and so on. At any point of time, if you want to find the chromatic number of this induced subgraph on some set S, what do? Well, you can find an independent. Remember, we are working in the exponential world, so don't worry about exponential time. We have to live with exponential time. So you can find an independent set in the graph and say, okay, I'm going to color this set with one color and then inductively color the remaining graph with new colors. Okay. And since I have doing bottom up, I have already computed the chromatic number of the small graphs, so I don't have to recurse. So for every T, which is an independent set, I give a color 1 and then find the chromatic number of the remaining graph, which is the induced subgraph of S minus T. Okay, that's it. That's a very simple dynamic programming, and eventually you will get the chromatic number of the whole graph. Okay, minimum over all these things. One can, easily prove the correctness of this equality here, that you're trying to remove independent sets, give them color 1, and then use your table lookup to compute whatever you have computed for the smaller graph. So again, as I said, this is also a nice college level exercise to give it for finding chromatic number. Now, how much time does it take? What is the running time of this algorithm? Well, the number of subsets for which you're going to compute this is 2 power n, because you're actually doing it for every subgraph of the graph. And to compute the chromatic number for each subgraph, you are running over all independent sets and then doing a table lookup. So the number of independent sets can be 2 power whatever the size of S. So naively, this is like 4 power n, but if you do it's already better than k power n we started out, because this is for any k, the chromatic number is. But if you are very careful about the analysis, it's not 2 power s, it is 2 power s, but that's not 2 power n for small sets, right? For small sets, it's small. So if you do a careful analysis, number of subsets of size I is n choose I. For them, you spend 2 power I time. And so if you do this, it's actually 3 power n. So this is already a good bound compared to the k power n bound we started off with. All this is, as I said, it's a nice exercise to do it in a grad level course. And this can actually be improved. Okay, I have some time. So you can improve it to something better, because instead of running over all possible independent sets, you run over all possible maximal independent sets. Then it turns out you can improve this bound from 3 to something better than 3. Okay, so let me just put that in. T in the min above can be over all maximal independent sets. there is a nice little theorem which tells you that in any graph on n vertices, number of maximal independent sets is 3 power n by 3, not 2 power n, which we used here. So instead of 2 power I, you plug in, put 3 power I by 3, and this gives you something better than 3 power n. Okay, so all this is pretty straightforward, in my opinion, for a grad level course, first course on algorithms, first course on complex analysis. And now I will spend the next 5-10 minutes telling you how this bound can be improved to 2 power n using fast Fourier transform, right? So it's a very counterintuitive connection. Where is fast Fourier transform and polynomials? You're talking about something on graphs, okay? So the idea is we can improve this to 2 power n using fast Fourier transform. So this O star notation means 2 power n times some polynomial in n, okay, which I'm ignoring because compared to 2 power n into 2 power n, this is much better. Okay, and again, if you're not sold on, do I really care about these improvements? My main point is to convey how something like fast Fourier transform is useful for designing algorithms. Okay, so the idea here is to solve, right? Somehow you want to convert your problem into something like a polynomial multiplication. Then you're done, right? That's all you want to do. Your chromatic number problem, you want to convert it into some small number of polynomial multiplications whose degree can be very large. So the polynomial we are going to write, each term corresponds to some subset. Actually, I wrote independent set, may not be independent set, it could be some I-colorable set. But the number of subsets can be 2 power n. So the polynomial degree can be very large, 2 power n. And using polynomial multiplication, we are going to gradually build I-colorable subgraphs for various values of I. Okay. So let me write this set. SA of I is all subset of vertices in my graph of size A, such that the induced subgraph on X is I-colorable. Now, what is SA1? Does anybody want to take a crack at this?
Independent set.
Exactly. All independent sets of size A, right? Because cardinality is A, one colorable sets are exactly independent sets. Simply all independent sets. Now, enumerating all this is all 2 power n. And 2 power n I'm willing to give you. It's just that I don't want to give you more than that. And what is the chromatic number in this notation? SAI.
One
only. No. Chromatic number of the whole graph. In this graph, I'm gradually building I-colorable graphs, right? So one colorable graphs in this graph are simply all independent sets. Of course, I have this cardinality constraint of A. Now, what is the chromatic number? Well, what is the minimum I for which the whole vertex set is I-colorable? Right? That's what it is. So it's minimum I such that SNI cannot have many sets. It will have only one set, the entire vertex set. And I'm looking for the minimum I such that SNI is non-empty. Okay. So this is it. So now we are going to compute this SAI for different values of A and I. And eventually, I will find when SNI is, what is the I for which SNI is non-empty. And that would be our chromatic number. And I'm going to do all this using some polynomial multiplication. Okay, so that's the big idea. Okay, I may not have time to get into all the details here, but here is this observation. If you have two polynomials of degree 2 power n each, the naive multiplication algorithm will take the quadratic, right? So it will be 4 power n. But using FFT, how much time will it take?
3 to the power of n.
Yes, sorry.
3 to the power of n?
2 to, no, FFT takes n log n. Remember, if the degree is n, using FFT, multiplying for two polynomials of degree n takes n times log n, right? Whereas here, n for us is 2 power n. And what is log of 2 power n? N. Right? Our logs are all to the base
N log
2.
2.
So it's basically n times 2 power n. That's it. This is the big advantage I'm trying to use to improve the running time from 4 power n, 3 power n to 2 power n. Because we're going to set up polynomials of high degree 2 power n, where the coefficients represent I colorable sets for various values of I. And we're going to keep multiplying polynomials to get I plus 1 colorable sets from I colorable sets. And all this multiplying polynomials takes only 2 power n times n. Even if I do some polynomially many multiplications, overall running time will remain 2 power n times polynomial. Okay, so that's the idea. Now, the exact details would involve a lot of notation. I'll at least quickly flash through the slides. So I'll explain how to compute SAI for various values. See, number of values of A is only n, because A talks about cardinality. Number of values of I is k, the chromatic number. So these are all some small numbers. So I can do n times k many multiplication. It doesn't contribute to the exponential running time. So for various values of A and I, we will just compute SAI from SAI minus 1 by doing a polynomial multiplication. Okay. So remember, SAI is the set of vertices of cardinality A, which are I colorable. Now, X, a subset of vertices X is an SAI, meaning that induced subgraph has size A and is I colorable. If you can partition it into two sets such that one is of size some integer B and it is I minus 1 colorable, and the other thing is of size A minus B and it's an independent set. Okay. Now, this is something, it turns out, you can find out from polynomial multiplication. So what you do is bin X, for any set, you can write the characteristic vector of this set in the vertex set. It will be a 0, 1, 1, 1, 0, 1 kind of an n-bit vector. Write the value corresponding to that, and let me call that as v of x. Then I'm going to have a polynomial of that much degree with exponent v of x. So consider the polynomial pbi minus 1, which contains all the sets which are I minus 1 colorable and of size b. And I'm going to write y power v of x. What is v of x? Write x in binary and compute its integer value, and that is the value here. Now, this polynomial will have high degree, 2 power n degree, because the characteristic vector can be of n bit and the value can be of 2 power n. Now, it turns out you can show that your set X is in SAI if and only if there exists an integer B such that in the product polynomial P B I minus 1 times P A minus 1 I Y, there exists a term whose exponent as A ones in the binary representation of Bx. Okay, this is mouthful of terms. I'm not going to try and explain it, but essentially you can compute these X's which are in SAI by doing a polynomial multiplication with some, you need to find this integer B, so you're going to try all possible integers, okay? But there are only about n of them. So with an I minus 1, n polynomials, and here this is fixed. Once I fix this is A minus B, an independent set. So I have to do something like n polynomial multiplications to get. Okay, so there's some explanation for it. Simple combinatorial expectation. So essentially, I'm saying SAI can be computed by multiplying some n pairs of polynomials, the n for different values of b, each of degree at most 2 power n. So it takes 2 power n times n square. This is for a particular A and a particular I. Now you have to try this for all possible A's and I's, but that's only some, another n and another k. So overall time would be 2 power n cubed k. Okay. And as far as I know, this is at least the 2 power n is the best possible running time known so far with some polynomial term. The quest continues. You can improve the base 2 to something even smaller than 2. There are a lot of problems for which this has happened. This tells you that even in the exponential world, when it's not enough to show that a problem is NP hard and forget about it. There is a whole hierarchy of exponential functions, so you can still think about improving the algorithm even in the exponential world. Okay, so good. I'm close to my time, so I'm going to conclude. Essentially, what I told you is this. I mean, I didn't give too much references here. So FFT goes back to Gauss and Fourier and various people, but this modern version of computing its running time and arguing that it takes n log n started in 1965 by a couple of authors. And in trying to improve the bit running time, there has been a lot of work on this. Now, this n log n is actually in the textbook. Okay, this Corman's book contains a chapter on fast Fourier transform. But people are learning about these modern applications now, like for graph coloring. Approximate string matching is another area where there's been a lot of very interesting applications. And typically the idea is to reduce your favorite problem which you're trying to solve to set up some polynomials and reduce the problem to some sort of multiplication of polynomials. Okay, I will conclude here. Thank you very much for your attention.
Venkatesh, nice to hear you, and it was a good presentation. And you gave two good applications of FFT. One, the instance of product of two integers using polynomial representations, and the other for the chromatic number. Now, my concern is when you take SAI, where A you talk about the size and I the colorable index. See, determining the independent sets itself is a NP-hard problem of the arbitrary graph.
Yeah, sure. But I'm allowing 2 power n time. That's not a problem.
Okay.
I'm running time allows 2 power n. That's not a problem. I'm actually trying to reduce from 3 power n to 2 power n.
Yeah, no, that I could see and understand. The other concern is, you mentioned about this bottom-up approach. Is there any advantage over top-down approach? Is it possible?
See, dynamic programming always works bottom-up.
Okay.
You set up your recurrences in a top-down fashion, but typically when I want to compute for a larger problem, you need solutions for the smaller problem, so which you should have computed and kept ready in the table look. So this is just a
basically this is an instance of this is also an instance of divide and conquer, is it?
Somewhat, but you don't want to recursively compute. You store the subproblems because recursion will take you exponential. I mean, bad time. Here we are working with exponential. In a typical polynomial time dynamic programming algorithms, if you do divide and conquer, it can lead you to exponential time because you will be recomputing the same problem multiple times, whereas dynamic programming allows you to store solutions for subproblems.
Are there FFT applications for approximate algorithms also? In graph theory context?
I don't know. But for example, approximate string matching, I know. There is a very nice. So for example, string matching problem is the standard. Given a pattern in a large text, you want to know whether the pattern appears in the text. This is the standard string matching problem. You want to match
any instance of graph theory?
I don't know. It may be there. I'm not sure. I don't know.
Thank you, Venkatesh. Nice talk.
Venkatesh, as usual, your talk has been well organized. And stands out as a polished edifice. So we are very thankful for that. But then I'll have to ask others to, whoever has questions can raise it now. Anybody else with questions? In fact, he has finished his lecture 5 minutes ahead to give more time for people, I suppose. So I think people should make use of it to ask any. I only have a very naive suggestion to the people who work in the domination parameters and all that. They can. It must have been done definitely for the standard domination parameters. The older ones. But people keep on introducing. Maybe they can try out these computing time algorithms on similar lines. Can take help from vegetation so that they can make their work more non-trivial and so on. Okay, this is just a suggestion to the young researchers who nowadays define various domination parameters for various reasons. Okay, and over to others.
I don't think I finished early. 11:45 was supposed to my.
Yeah.
Yeah. Yeah. You closed it at 10:40, I suppose. Is it?
No, 10:44.
Okay. 10:40. Okay. Fine.
He was almost.
Yeah. He's a seasoned speaker, so
that is right.
He starts at that right time and finishes at that right time.
That's the fact. That's the fact.
Unlike people like me, so I envy. Okay. Sir, you can ask.
So many conclude.
Okay.
In that case, can I take your permission to start our the next session a bit early, or is there going to be?
No. There are some instructions by the desk. Now let us close this first, and then they will give some instructions and so on.
Okay.
Thank you again.
Thank you, Venkatesh. Thank you very much.
Yeah.
Thank you. It was nice seeing you all.
Thank you. It's a very nice lecture.
Thank you. Thank you, Professor. Ranjini, please. Ranjini?
Yes, sir.
Please.
Thank you, sir. Thank you for the bright ideas and such an informative session. Thank you for, I also thank Professor Dr. S.S. Somasundaram who chaired the session. Now we have the paper presentation session which begins at 12. Participants who are scheduled for today's link can join through their respective links. I also request the participants not to log in through several links to avoid unnecessary interruptions. I repeat, I also request the participants not to log in several links to avoid unnecessary interruptions. Thank you.
Information for the papers being presented in 4 sessions.
Ma'am, we will send it now, ma'am. Just a minute, ma'am.
Madam, I am not getting it.
See what happens, participants who have to present the paper, they will be logging respectively. They must be knowing that this one. But suppose I want to attend any session, I will attend the session where I am interested in the papers. Nah? So all the 4 sessions, what are the papers being represented? Yesterday I had a talk with Asim. He said he will send me all by Gmail, but there is no, so far there is nothing on Gmail. I cannot join all the 4 sessions, no. Like that becomes difficult, no, because you will go fast, rolling fast.
I think all the list has been published in the website itself, and people can download.
It is there in the website. Okay.
Yeah, it is in the website. Yeah, it is in the website right from 9th evening.
I have not seen.
Every session details are being uploaded, and it will be the correct place where we get exact data. The personal communication may not work well.
Maybe I have to check it and I will see it.
Yeah, please, madam. Please.
At what time the
Ranjini, please display one by one. 5, 6, 7, 8. Yeah. You are muted. Ranjini, you are muted. You please unmute yourself.
These are the paper questions for session 5.
6.
Sham, wait a while. Sham, wait a while.
Okay, this is session 6.
Seven.
7.
Go to 7.
Session 7.
Okay.
Session 8.
I will attend 8. Can I attend 8?
The same link you attended yesterday.
Yeah,
4, 8, 12 are follow the same.
I will be able to find out that link on the.
Okay, we will post it in the chat box.
I have posted it because yesterday chat box may not be available. No?
Oh, yeah.
Just post it on the. Yeah.
Wait a minute, we will post it.
Okay.
Yes, Sherry. Yes. I will. And there are.
Oh, it's too big.
Those who wish to join other than session 5 ask to leave the Zoom meet and join the respective sessions. Participants who are going to join other than Google Meet requested to leave the Zoom and join in the Google Meet so that we can avoid audio interference.